Today I am going to start a very important theorem which is called a closed graph theorems. So first the name of the theorem, so which is a closed graph theorem. So which is a closed graph theorem. This theorem is very important for a examination point of view. Also it is important for application. So first we understand some definitions. So first definition is a graph of a function. So first definition, graph of a function. So we already know that the function is a mapping in which every element associate to a unique element of the right hand side. Let x and y be any two non-empty set, be any two non-empty set. Let x and y be any two non-empty set, and f is a mapping from x to y with domain capital X and codomain and range, not codomain, range y. So this is a mapping from x to y in which x is domain and y is a range. So this is a such kind of situation. So this is a x and this is a y. X is a non-empty set domain and y is range, and f is a function from x to y. So if x is some element belongs to capital X, then its image f of x belongs to capital Y. So graph of f is a set in a tuple form. So what is definition of graph of function f? Graph of function f. So it is a set. This is a set in tuple form x comma fx such that this x belongs to capital X. So this is a tuple form such that x belongs to capital of the. This is called graph of f, and also it is denoted by fg. So this means it is a graph of f. Now next definition is, this is a graph of x. Next definition is closed linear transformation. Closed linear transformation. So we already know that the linear transformation. So next definition is closed linear transformations. Suppose n and n dash be any two normed linear space. Normed linear space. So N and N dash is a norm linear space. A linear map T from N to N dash. So this is a mapping, linear mapping T from N to N dash is said to be closed. Is said to be closed if for every sequence xn, this is sequence, belongs to n such that xn approaches to x as n approaches to infinity, and its image under T approaches to y, then both it implies x is also belongs to n and y is equal to T of x. It means Txn approaches to T of x and x should be a part of n. X should be a part of n. So this is called a definition of closed linear transformation. If any sequence in n approaches to x and its image approaches to y, then y is equal to T of x and x is a part of that n. That n means n normed linear space. Now, the statement of the first theorem, so which is very important. So, statement of first theorem. So, first understand the statement. A linear transformation, transformation is a closed, a linear transformation is a closed if and only if its graph is closed. If and only if its graph is closed. So this is very important result expected for examination. So if a linear transformation is a closed linear transformation, if and only if its graph is closed. Now, how we can write this theorem? So let n and n dash be normed linear space. Normed linear space. Let n and n dash be a norm linear space. And suppose T is from D is a domain D to n dash is closed linear transformation. It is a closed linear transformation and D is a domain part of n. So remember that this is a part of n. So in first part, my claim is its graph is closed. What is its graph? T of G, which consisting x comma tx such that x belongs to D. So our claim, its graph means Tg, which is a closed. So that is my purpose. So this is a given, it is a closed linear transformation, and my aim is to prove that its graph is closed. So how we will prove any set is a closed set? So we will take a limit point, then prove that it belongs to that set, then it means it is a closed. So in that case, what is Tg? So Tg basically is subset of n cross n dash, n cross n dash. So I take x comma y be a limit point of Tg. So this is a limit point of Tg, right? So it means if it is a limit point, so there exists a sequence xn comma txn, and this sequence in T of G such that this sequence xn comma txn, it approaches to x comma y as n approaches to infinity. So from the first step, if it is a limit point, then there exists a sequence which satisfies this condition. So from this, it implies norm of xn comma txn minus x comma y approaches to 0 as n approaches to infinity. Again it implies, so here we use the definition of the norm. So first in this step, which is xn minus x comma txn minus y, this norm approaches to 0 as n approaches to infinity. Now in the next step, it implies, now using the definition of norm, so this will become xn minus x plus txn minus y approaches to 0 as n approaches to infinity. Again it implies, now if sum of two positive terms is equal to 0, then each term is 0. So it implies norm of xn minus x approaches to 0 and norm of txn minus y approaches to 0 as n approaches to infinity. So it implies xn approaches to x and yn, xn approaches to x, number 1, and number 2, txn and txn approaches to y. as n approaches to infinity. Also, we know that this T is closed linear transformation. Closed linear transformation. If it is a closed linear transformation, then by definition of closed linear transformation, it implies x belongs to D and y which is equal to T of x. Y which is equal to T of x. So what we get? We get this xy. Basically, it is nothing. It is x comma dx, where x belongs to D. It means this belongs to graph of G. So it implies this xy, which is a limit point, belongs to graph of G. So it implies graph of G is a closed set. It is a closed set. So if operator is closed, then its graph is closed. If T is closed, then its graph is closed set. Now converse part. Conversely. Now in the converse part, its graph is closed. Now let Tg is closed set. Closed set. If Tg is closed set, now my aim is to prove T is closed linear transformation. So our claim T is closed linear transformation. Closed linear transformation. Now to prove it is a closed linear transformation, I take a sequence in its domain. So if I take xn is some sequence belongs to domain of D, and this sequence xn approaches to x and its image txn approaches to y. So that is a given part. So it means this xy is a, because xn comma txn, it belongs to tg because xn belongs to D. So since this sequence xn comma txn, this sequence is contained in T of G, then it implies this xy is the limit point, the adherent point, limit point of Tg, right? So it is a limit point. Even I can use it is a adherent point, because adherent point of Tg. If it is a adherent point of Tg, so it implies this xy belongs to Tg closure. So it belongs to Tg closure, but Tg is closed, so it means this is equal to Tg. Why? Since this Tg is closed set, if Tg is closed set, then it implies this x comma y belongs to Tg. So what is the construction of Tg? Which is x comma Tx, x belongs to domain. So this is a construction of, this is a definition of Tg. It means xy is a element of this kind. If element of this kind, then it means x belongs to D and y is equal to Tx. So it implies T is closed linear transformation. Closed linear transformation. So that is our result. So this is a proof of first theorem. Now next is main theorem. So which is called a closed graph theorem, which is called a closed graph theorem. So remember that in the examination, examiner will be asked as state and prove closed graph theorem. So remember the statement of these theorems. If B and B dash, if B and B dash, this is a Banach space or Banach space, if this is a Banach space, and if T is linear transformation, T is from B to B dash is linear transformation, so it is a linear transformation, then T is continuous, then T is continuous if and only if and only if graph of T, this is a graph of T, is closed. So we can also write in the graph of T is closed, or we can write it as Tg is closed. So we know that what is Tg? Tg is a graph of this values. Now, so first I will change the background color. So now this. Now this is a statement, and this is very important result. In the examination, it will be asked as state and prove closed graph theorems. Now first part, if T is continuous, then its graph is closed, and if its graph is closed, then T is continuous. It is a if and only if part. Now I start from this, let T from B to B dash be a continuous linear transformation. linear transformation. I start from continuous. Linear transformation, we can also write it as LT. And my claim, our claim, so just divide the theorem into two parts. One is given and second is to prove. So my claim is TG is closed. TG closed means its closure is equal to TG. Okay. So what is TG? I just write it here. It is a set in tuple form x comma tx and x belongs to B. So just write. So that is my aim. TG closure is equal to TG. So this right hand side is a subset of left hand side, we know that. So my aim is to take one element from this set and belongs to this set, TG. Let x comma y, it belongs to TG closure. So it implies by definition. So what is it? It is an adherent point. So xy is an adherent point of TG. So by definition, there exists a sequence xn comma txn, this sequence in TG such that xn comma txn, it approaches to xy as n approaches to infinity. So this is my given part. Now from this, if it approaches to 0, it means norm of xn comma txn minus x comma y, this approaches to 0 as n approaches to infinity. So it implies this is xn minus x comma txn minus y, this approaches to 0 as n approaches to infinity. Again, so second step. So just go step by step. Now it implies norm of xn minus x approaches to 0 and norm of txn minus y approaches to 0 as n approaches to infinity. So it implies since, so it implies xn approaches to x and txn approaches to y. Now we know that since t is continuous, so by definition of continuity, if xn approaches to x, then its image approaches to its image. So by definition of continuity, its image approaches to its image. So that is the theorem in the basic topology of Walter Rudin. So first chapter, basic topology of Walter Rudin and then after continuity. So that is in the chapter of continuity. So if xn approaches to x, since t is continuous, so its image is converge to tx. By using the concept, if a sequence converge, then its limit is unique. By using the concept of uniqueness of limit, so tx can be written as y. If tx can be written as y, so it implies x comma y, which is in this form x comma tx, and this belongs to d of g. So that is my aim. So xy I take from tg closure and it belongs to t of g. So tg closure is part of t of g, and it implies tg closure, which is equal to t of g, and it implies this tg is a closed. tg is a closed. So graph, we get this graph is a closed. So this is a closed graph theorem. When we combine the previous part, so it will be the t is continuous if and only if it is a closed. Now converse of this theorem. So we did only first part. So now we are going to start converse of this result. So in the converse part, so what is given? Given is let tg, which is contained in B cross B dash, be a closed subspace, be a closed subspace. So which is a closed subspace. Then next is to prove. Next is to prove. If it is a closed, then my aim is t is continuous. T is continuous. Also, I can also show that t is bounded, because bounded operator are continuous. Now in the given part, the graph is closed. This is a closed. Now this closed is a part of B cross B. So this B and this B. This is a Banach space. This is Banach space. Then this entire is Banach space. If entire is Banach space, then Banach space, this is a complete. So this is a complete. On the other hand, this tg, so this tg is a closed, which is a part of this. So this is a closed subspace, right? Now remember a result, closed subspace of complete metric space are complete. So I repeat, closed subspace of complete metric space are complete. So this will be complete. So this will be complete. If it will be complete, then it will act as a Banach space, because it is a part of norm space. Now it is complete. So this is act as Banach space. Banach space, right? So it was already norm linear space. and closed. Since closed subspace of complete metric space is complete, so it will act as the Banach space. Now I define a mapping phi which is from Tg to B. I define this mapping. If I define this mapping, this is by, now what is the element of Tg? This is x comma Tx, and what is the element of B? That is x for every x belongs to B. So this is equation number 1. Now my aim to prove it is a bounded linear transformation. So my aim to prove that it is a bounded linear transformation. So first of all, I will prove it as a linear transformation. So to prove it as linear transformation, also 1 1 and on 2. So that is clearly. So I take, let first two element, one x comma Tx and second y comma Ty, and this is belongs to Tg, and alpha beta are scalars. So remember that this is a, if this is a complex scalar, it depends upon the given Banach space. So if it is a complex valued Banach space, then it is a complex scalars. Now phi, this phi which is equal to alpha x comma Tx plus beta y comma Ty. So this value can be written as, this is phi. So here I used scalar multiplication. So just note each step. I used scalar multiplication. So it will be alpha x comma alpha Tx plus beta y comma beta Ty. I used this concept. Now in the next I will use the sum of tuple. So what is the sum of tuple? So this is equal to phi, which is first is alpha plus beta y comma alpha Tx plus beta Ty. So tuple, and this is in this bracket. Now T is a linear transformation, right? So first phi, which is alpha x plus beta y comma T of alpha x plus beta y. Why this is possible? This is possible because in the given part T is a linear transformation. So this can be written as in this form. Now using the definition of phi, so by using the definition of phi, this will be alpha x plus beta y. Now again using the definition of phi, so this will be phi x comma Tx plus beta, which is phi y comma Ty. So it prove our first part. What is first part? So first part is this mapping phi from Tg to B, which is a linear transformation. Linear transformations. Now, next is T is 1, 1, and third is T is onto, and then T is bounded. So we are doing all these things. Now in this case, to prove 1, 1, let phi x comma tx, which is equal to phi y comma ty. It implies, using definition, so this will be x, using definition this will be y. It implies x comma tx, which is equal to y comma ty. It implies this phi is 1, 1. This phi is 1, 1. So from this we find that this phi is 1, 1. Now next is phi is onto. Now just see this phi mapping, which is from Tg and this is from B. Its element is x comma tx and its element is x. Now just observe the definition of onto. For every x, if x exists, then x comma tx also exists, because x is directly related to x. So it means clearly this mapping is onto. So if I write in a definition, then we can write it as for every x belongs to B, there exists x comma tx, which belongs to T of G, and such that phi of x comma tx, which is equal to x. So it implies this mapping is onto. Now phi is linear transformation, phi is 1, 1, and phi is onto. So it implies phi is linear transformation, and next is 1, 1, and third is onto. So it satisfies all the conditions. Now next, to prove phi is bounded linear transformation. So very simple. Norm of phi comma x comma tx, this. Now just substitute its definition. So this is norm of x. So simply substitute its definition. Now this can be written as norm of x plus some positive number, which is norm of tx, right? This can be written in this way. Now what is this? It is a norm of x comma tx. So this is definition. So what we get? We get norm of phi x comma tx, norm of phi x comma tx less than equal to, here k is 1, so norm of x comma tx for every x comma tx belongs to tg. So it means this phi is a bounded. This phi is a bounded linear operator. Since bounded are continuous, so also it is a continuous. Also remember that. Also remember that it is a continuous. Now, in this case, so we prove that phi is a bounded linear operator. Now, since it is a 1 on 2, so its inverse exists. So here phi is from Tg to B. So it is a 1 on 2 invertible. So phi inverse from B to Tg is also bounded linear transformation. Bounded linear transformation. Clear? Because phi is bounded linear transformation 1 and on 2. So its inverse is also bounded linear transformation. Clear? So what is phi inverse x? So phi inverse x, and this is a, by definition, phi inverse x, which is equal to x comma tx. So remember this, phi of this is equal to x. So phi inverse x, which is equal to x comma tx for every x belongs to G. For every x belongs to B. So this is a bounded linear transformation. So remember that. Now phi is bounded linear transformation. So if it is a bounded linear transformation, so we here write it as norm of Tx, which is less than equal to norm of x plus norm of Tx. I can write it as for every x belongs to B. So why I can write it as? So first understand. I write it as because this is a some positive number. If I add some positive number to this, it will always be greater than equal to itself. If it is 0, then equal, otherwise greater. So what is this norm? It is nothing. It is a norm of x comma tx. It's nothing. It is a norm of this values. So just I used less than equal because that is, so this is less than equal to, so this total sum is equal to this values. This total sum is equal to this value. Now this value is equal to norm from this, which is a phi inverse of x. And what is phi inverse? It is a bounded linear transformation. So by using the definition of bounded, this is norm of phi inverse into norm of x for every x belongs to B. So by using the definition of bounded linear transformation. So what I get? I get this norm of Tx which is less than equal to norm of phi inverse, so take it as constant, into norm of x for every x belongs to B. So it implies this T is bounded operator. So this is a bounded operator, and we know that every bounded operator is continuous. So T is continuous. T is continuous. So which prove our result? Which prove our result? Ki if graph is closed, then T is continuous, and if T is continuous, then its graph is closed. So that is our result. So next theorem related to this closed graph theorem we will discuss in the next